The Advanced Sensor Instrumentation Program vision is to develop advanced sensors and instrumentation to address critical technology gaps for monitoring and controlling advanced reactors and fuel cycle technologies. Our goal is to provide cross-cutting research that contributes to the success of the NE R&D programs by obtaining the needed I&C technologies that support experiments, deliver unique sensors and related technologies for each reactor technology concept and fuel cycle facility. Also research that enables the broader mission of the Office of Nuclear Energy by supporting common I&C technology development objectives. And research that can overcome current barriers to nuclear energy system deployment. This includes research that resolves technology gaps, enhances functionality, and provides focused demonstration of advanced technologies to provide science-level evidence for acceptance. This program provides a new model of I&C research development, one that is more collaborative, coordinated, and designed to meet the needs of many programs at once. In the ASI program, we have 4 areas of research. Advanced sensors to develop a fundamental understanding of sensors performance and to improve physical measurement accuracy and reduce uncertainty. The second area is digital monitoring and control to provide increases in control systems performance and self-calibration capabilities. The third area is nuclear power and nuclear plant communications to research and develop communication technologies needed to support greater data generation and transmission demands while maintaining reliability, resilience, and data security. The last area is advanced concepts of operation to develop and test higher integral control system architectures where new human-system interaction is defined. Research in these areas needs to support the DOE NE R&D programs listed on the site, at least 2 of them. And last year, we conducted a poll of these programs on their I&C priorities, and these areas are still valid. For this solicitation, we're going to be focusing on the digital monitoring and control area. Okay, this year's topic is digital technology qualification demonstration for embedded digital devices. As more and more small components include embedded digital devices, it presents a challenge for the nuclear industry. As products are upgraded over time, they provide new capabilities and therefore new market opportunities. But they also introduce the risk of software failure and software common cause failure. Sometimes the purchaser isn't even aware that the replacement device offered as a like-for-like replacement has now an embedded device in it. The phenomena is nothing out of the ordinary since we experience in our daily life. Refrigerators, TVs, and other appliances now include embedded processors. However, in nuclear, the presence of these embedded digital devices create a whole different set of concerns and regulatory requirements. This issue is one that is affecting existing plants, will affect new builds, and without a proven resolution methodology that is robust enough to scale to future devices, it will also affect future nuclear reactor and fuel cycle systems designs that rely on digital I&C technologies. Therefore, this project goal is to develop a testing methodology that eliminates the possibility that there is a software common cause failure so that it doesn't have to be considered in the qualification of the component or the system in which the component resides. As of now, the NRC has not endorsed through safety reviews nor regulatory guidance any form of testing that would practically eliminate consideration of software common cause failure. Thus, to meet the regulatory requirements, if a device is conceivable subject to software common cause failure, then a diverse system may be needed to satisfy the accident analysis acceptance criteria during the occurrence of the assumed software common cause failure. For the proposal requirements, even though most components should be universal and apply across the board to different reactor types, I want to emphasize that as a cross-cutting program, we will be looking for proposals that show how this research can benefit multiple reactors and fuel cycle applications. And it requires a project should include a partner from industry. There are two types of partnership that would be helpful. If you are not a component supplier, teaming with one to test the methodology on a real commercial device would validate a lab fabricated device. Once the device has passed laboratory bench testing, applicants should work with a utility or a third-party qualifier to ensure that the methodology will meet all the requirements for qualifying the device as fully qualified for safety-related applications or as commercial-grade items dedicated for safety-related applications. There are many technical challenges that need to be addressed to provide this demonstration, and we're focusing on the following ones. Proof of acceptable software operational reliability. The NRC has indicated that certain simple digital components might be exempt from consideration of software common cause failure. The definition of simple is still under debate. According to the recent NRC update presentation by Dr. Steve Arnn, the NRC appears to be headed towards the definition as every possible combination of inputs and every possible sequence of device states are tested. Therefore, the qualification method proposed would assume that we can test the device for all combinations of inputs and internal state sequences such that any type of fault that might affect simultaneously all identical devices will be identified and corrected. This has been proposed by at least one nuclear power plant, but did not prove feasible in the past. Finding a solution for this problem would provide a significant benefit to the nuclear industry. Next up, U.S. nuclear regulatory requirements, the NRC regulatory requirements. The draft regulatory issues summary, RES, is expected to be published later this year. It has been the topic of discussion at NRC industry meetings facilitated by NEI, for example. The draft RES has a long list of applicable regulations and guidance documents. You can get a copy of this document using the accession number provided here. Another challenge is the ability to detect defects introduced through the entire supply chain. For safety-related components, the entire life cycle of a digital component is required to be under a software QA program that is intended to greatly minimize the introduction and lack of detection of software defects. In the case of a dedicated commercial-grade item, the continuous application of an NRC compliant QA program is not assumed. Therefore, a testing methodology that can find defects of any type or origin and does not rely on past QA program application is needed. For example, the manufacturer of a nuclear component acquires an embedded digital device from a third party and does not know where or how comprehensive the testing was done for this device. So how can we assure, or they assure, that all defects are detected? That's a challenge. Next challenge is ability to dedicate commercial-grade devices for safety-related usage. This is closely related to the last requirement. For example, take a device that wasn't intended for nuclear usage and that conforms to other quality requirements of the industry standards, ISO, etc., and subject it to methodology for the nuclear requirements listed here. For example, show how a smart pressure transmitter that was developed for use in process plants can be used in nuclear power plant safety-related applications. Next one is cost-effective and broadly applicable to multiple small plant components. It is understood that nuclear-grade components cost a lot more because of the expense of the qualification testing. But in this case, its costs are much more higher than the legacy analog counterparts. It won't be used. For example, testing a certain component with an embedded digital device that costs several million of dollars cannot compete with its analog counterpart that only costs around $1,000. You will need to provide a cost-benefit analysis to show if it is competitive. Also, you need to avoid very specialized tests for one specific component. They cannot be applied to a broader range of components. And with that, in conclusion, some expectations for this FOA. As you plan for your proposal, I want to stress out that we're looking for advanced INC technologies that will aid in the reactor and fuel cycle development, improve economic and safety, demonstration of proposed technologies in a setting that represents the nuclear power industry, and innovative and revolutionary cross-cutting technology that can be applied to multiple reactor designs and fuel cycle concepts. Here is our contact information. Bruce Halben from the Idaho National Laboratory is my technical lead for this program, and he'll be on the phone to help answer any technical questions. So, are there any questions?
Okay, we'll start with the first question then. Is radiation-induced hardware failure considered in this year's topic?
Not specifically. I think that we're interested more in the software and dedication aspects of the embedded digital devices. We have funded research, and we are sponsoring research right now related to radiation-induced failures.
Are there any specific sensors that have priority to other types of sensors?
We're not looking for sensors specifically. This is for any type of digital embedded system. So if it's anything that you can test and provide a methodology, then we're open to.
We don't have specific sensors or types of sensors with embedded digital devices in mind at this time.
Is nuclear plant communication related to wireless communication of interest?
For this specific call, it's one of the topics in our areas of research, but for this one, we're concentrating on just one topic on digital technology.
What is the appropriate technology readiness level for this hardware development?
It should be at a fairly high technology readiness level. The NRC, especially if you look at the NRC industry interactions on this issue, we're interested in technologies and methods especially that could be used now and could be demonstrated soon. That doesn't preclude technologies that could be developed within the next, 2 to 3 years, but that's more the time frame that we're thinking about. It's something sooner rather than later. Subel, do you have some thoughts on that?
This is a demonstration project, so if you have it ready to demonstrate, then you need to let us. We don't have any specific.
The project, I'm sorry to interrupt, Subel. The project duration in here, I think the FOA call says up to 3 years, and Subel is right. This is a demonstration project, so it ought to be something that could be accomplished within that 3-year time frame.
Is there any interest in sensors for monitoring waste forms on storage?
Not under the current code. It won't fit under this topic.
Is materials development for sensor applications considered?
Again, that wouldn't fit under this specific topic for us.
What is the technical basis of the U.S. NRC testing requirements?
You probably need to go to the NRC website or talk to one of the NRC people. I talked to them. They're willing to. They have a lot of public documents and requirements, so it's a lot of information if you go to the NRC website.
As a follow-up to that question, if a better basis could be found, would this project be open to it?
Sure. Because this problem hasn't been resolved. It's an issue that the industry is dealing with right now, and yeah, we're open to any suggestion. You have a better idea, so yeah, let us know.
I would also add to that it would be important to bear in mind whatever the proposed new basis is how it addresses what the NRC and the industry position is on responding to the NRC's position for qualifying embedded digital devices. So we're not proposing that we enter into a research project to change regulatory rulemaking, but rather if the research proposes new ways to satisfy that or address that, that could be considered.